I'm Themistoklis Sapsis. I'm professor of mechanical and ocean engineering at MIT, and I'm also affiliated with the Institute for Data Science and Society, and as well as the Center for Computational Science and Engineering. At MIT, I teach courses that focus on dynamics as well as statistical modeling, stochastic modeling. My work is motivated from problems in ocean engineering. I'm a naval architect and ocean engineering by training, and ocean is characterized by both strong uncertainty, many factors that have uncertainty, random waves, random environment in general, but also complex dynamics, right? So when you have a structure, because it is subjected in big waves, for example, the motions can become highly nonlinear. So that creates a strong need for new mathematics, for new ideas in terms of modeling. And that was also always fascinating to me. For these reasons, we try to develop new techniques that allows us for prediction, and extreme events is one of the most important areas where, again, there is a real need in ocean engineering and more general environmental engineering. So, in relation to extreme events, we're working in three different areas with strong overlap, though. One is prediction of extreme events, probabilistic quantification is the second, and then mitigation or decision making related to extreme events is the third one. Prediction, when we talk about prediction of extreme events, we are more or less thinking about short-term prediction, right? So you have a complex system, whether this is a ship and you're trying to see what wave will be the most dangerous, so that you can, if you know this wave, then you can design the ship so that it can withstand this type of wave. But of course, the problem of prediction for extreme events goes way beyond the ocean. Another example is a dangerous maneuver of a helicopter, right? And you may lose lift during this maneuver, so the pilot needs to know that, or you may need to have an algorithm that will prevent that. So in all these cases, you have a chaotic system, like the underlying dynamics are really complex, chaotic in most cases, and the equations are so expensive that you cannot really solve them in real time. So what you need to do is to be able to derive precursors, as we call them, or characteristic signals that precede this type of extreme situation, and you are able to characterize the extreme event or forecast the extreme event ahead of time, again without having to deal with all the computational cost of solving the full order equation. The second problem of statistical quantification involves more about the long-term behavior of a complex system. Like examples in this case is what is the probability of a heat wave in a specific region, under the new climate, under climate change, or what is again the probability, the fatigue rate for a structure that is subjected to random waves. Again, in this case, the problem is that the models that we have, the computational models that we have, are very expensive to run for really long time until you get these probabilities correctly. So you have to develop the appropriate mathematics that will be able to tell you from short time series or from short simulations how you can extract conclusions about, again, the probability of an extreme rare event. The third area, as I mentioned, is decision making and mitigation of extreme events. And in this case, we're trying to develop algorithms that will be able to deal with these rare and very unexpected extreme situations. This can be an extreme anomaly, for example, in the environment, and where you want to send your vehicles, your autonomous vehicles, to reveal it, to explore it, to monitor it. Typical algorithms will try to focus on things that happen, very, very often. If you have an anomaly, a very rare anomaly, you need special algorithms so you can pay the appropriate attention to these things. And again, this is one of the areas that we put a lot of effort on making it happen.